Hello, we Group 11 and here is a presentation for a review meeting 4.
This is our final system sketch.
We measured the pump performance and found it's stable at max power but does not respond linearly to PWM input from the board, which makes sense considering its construction. Instead, it exhibits 3 response levels: max power, a single mostly stable middle level, and off.
A problem we encountered is that the pump overheats quickly when running at maximum power, as you can see in the plot on the right. For this reason, we created a code with modulated power for the pump and the cooler, which you can see on the left. The optimized cooling system improves the cooling rate by approximately 8-fold. Here we can see a snippet of the code. In the previous slides, we see that the temperature is oscillating above the target temperatures. Since we don't have more time for calibration, we can manually set the target temperature in the code to be 1 degree lower to get the wanted result.
Since last time, we did 2 series of OD sensor calibration, and they're both combined and showed in the graph to the left. We see that we have actually quite a big spread, but there are 2 sets of outliers, and both of these sets of outliers are from consecutive measurements. So we believe that it might have been air bubbles in our system while we were doing the measurements that resulted in these outliers, and we therefore decided to remove them, which leads us to the plot on the right, where we have a much nicer fit, and we have a 95% prediction interval of 13,500, which is good for what we want to use it for. This is a schematic of how our algae feeding system works. It basically works by first pumping water into our OD sensor. Then we wait for the water in the OD sensor to stabilize. And while we wait, we run a mathematical model that predicts how much the mussels are going to eat in the next 5 minutes. Then we measure what the concentration of the algae water in our OD sensor. And we combine that with the prediction to pump just the right amount of algae water into our mussel tank.
This is the mathematical model of our setup. The concentration of algae in the mussel tank decreases according to the mussel's filtration rate, which also depends on the concentration, thus forming a differential equation. What we need to find is the amount of algae we need to transfer to the mussels in order to keep them fed and in stable conditions, described by the goal concentration. To find the optimal volume of feed, we use gradient minimization. The function we minimize is the future concentration in the mussel tank, which we find by numerically solving the differential equation using RK4. This code needs to run on the board every time we feed, so we rewrote it in C and achieved a 37 times speedup.
To verify that our mathematical model works, we did a simulation of our control algorithm, which is what we see on the left. We see that first we feed the mussels, then the mussels consume, we feed the mussels consume, and so on and so forth. We decided to keep the average concentration slightly higher than the goal concentration, simply because the slope is smaller with a higher concentration than it is with a lower concentration, so we are a little more in a safe range. And then we see on the right a plot of the amount of water from the algae tank we pump according to the concentration of the algae tank, and this is simply to show that our algorithm corrects for the concentration of our algae water.
Since the system can now be run fully autonomously, the remote control is no longer necessary. We instead opted to make a function to switch between auto and manual mode. When in manual mode, the feeding pump will be controlled using the sliders here, and when in auto mode, the feedstock is controlled using the built-in simulation, and the interface will simply be used for live displaying the data.
Regarding system safety, all electronics were handled properly and put in plastic casings containing dehumidifiers. Biocompatibility of used materials was analyzed, and the research and toxicity of our plants was made.
We tested the biocompatibility of 2 materials used in our system, the watertight seal for the OD sensor and the net used to hold mussels. The goal was to see if either material affects algal growth. For each condition, control, plastic and net, we measured the initial algal concentration, submerged the material in separate vials, and ran 3 replicates per group. The experiment was intended to run over 24 hours, but due to time constraints, we ran it for 6.5 hours and then projected longer-term growth in the graph. Growth rates were calculated as the mean across replicates, with standard deviations included in the analysis. From the graph, we can see that all 3 conditions show similar growth, indicated that the materials are indeed biocompatible.
For the ammonia experiment, we got data from another group. We used this data to estimate how much ammonia the 3 mussels in our bucket in total would excrete. Based off of the total mussel weight in our bucket, the mussels would excrete approximately 0.17 parts per million ammonia per hour. This ammonia can be used as nutrients for our plants or partially feed the algae.
Since the previous review meeting, we have improved our insulation. We added a layer of repurposed cardboard around the bucket and then a plastic foil to prevent the cardboard from becoming wet. We then ran the insulation test again and obtained an improved cooling rate with the new insulation, meaning that the test was successful.
And here are the plants that we found on the beach, which we used in our model.
Here are some future improvements we would have liked to do if we had more time and resources. And the main thing here is watering the plants with the mussel water.